All right, today we're jumping into a fantastic tech blog from Netflix. We're going to break down a concept that is just so important for anyone trying to innovate. How do you make sure a brilliant idea doesn't get tossed in the trash just because your test wasn't strong enough to see it? So let's just start with that high-stakes question right there. What happens if you got a game-changing new feature, but your experiment, your A/B test, just isn't powerful enough to see its positive impact? Well, that brilliant idea gets marked as a failure, and it might just vanish forever. And this leads us right to the first big concept we have to get our heads around. It's a specific kind of mistake that, keeps data scientists and product managers up at night. That mistake is called a false negative. The easiest way to think about it is this. Imagine showing a test a crystal clear picture of a cat, and the test says, nope, no cat here. The effect, the cat, is obviously there, but your test just flat out missed it. In the world of product development, that's a new feature that really does make things better, but your data says it's a dud. And just like that, a huge potential win is gone. Okay, so how do we fix this? How do we build a better cat detector for our ideas? Well, the answer is this really cool concept called statistical power. Power, at its core, is pretty much the strength of your test's eyesight. It's the probability that if there is a real difference, a real improvement, your test will be sharp enough to actually see it and say, hey, look at this. It's your chance of getting it right. And the math here is beautifully simple. Power is literally just 1 minus your false negative rate. They are two sides of the very same coin. So the more power you have, the lower your risk of missing something great. It's all about building confidence in your results. Now, to really make this stick, let's use a simple analogy that comes straight from the source material. We're going to forget all about tech and products for a second and just talk about flipping a coin. So in pretty much any experiment, you start with the default assumption. Scientists call this the null hypothesis. For us, it's just that the coin is totally fair, a 50-50 shot. But we suspect something's up. We're testing against an alternative hypothesis, the idea that this coin is actually rigged to land on heads 64% of the time. So, to bring it all together, statistical power in this little game is just the probability that our experiment, flipping the coin 100 times, will correctly spot the trick. It's our chance of successfully calling out that unfair coin. And it turns out, for this very specific experiment, 100 flips with a coin that's biased to hit heads 64% of the time, the statistical power works out to be 80%. But what does that 80% actually mean? Well, it means if we ran this exact same 100 flip test 5 times, we should expect to correctly figure out the coin is unfair in 4 of those tries. But that 5th time, that's when we'd get a false negative. We'd look at the data and say, nope, looks fair to me, and we'd be wrong. Okay, so 80% is pretty good, but what if we want to be even more sure? How do we juice up the power of our tests? Well, the Netflix team points out that there are basically 3 big knobs we can turn. Those 3 knobs are the size of the effect you're looking for, the size of your sample, and the natural randomness or variability of the thing you're measuring. Let's break each of those down real quick. First up is effect size. And this one is just common sense, right? It's way easier to notice a massive earth-shattering change than a tiny, subtle one. A feature that doubles how much people use your app is going to be a lot easier to spot than one that nudges it by like 0.1%. Second, we've got sample size. The more data you collect, the clearer the picture gets. You'll get a much better read on a coin's fairness by flipping it 1,000 times instead of just 10. For A/B tests, this means the more users you include, the more power you have to see even those really small, subtle effects. And number 3 is metric variability. The best way to think about this is noise. If the thing you're measuring naturally bounces around all over the place, it's really hard to hear the quiet signal of a small improvement. So the less noisy your data is, the more clearly that signal can stand out.
But here's where it gets really interesting. You can't just turn the power dial all the way up to 100% without causing a whole other set of problems. It turns out this is a very delicate balancing act.
And that's because there's this fundamental trade-off between the 2 big types of errors. A false positive means you launch a new feature thinking it's a winner when it actually does nothing. A false negative, which we've been talking about, is when you miss out on a true winner. If you get super aggressive trying to avoid one, you automatically increase your risk of making the other. The way the industry usually handles this trade-off is by setting a limit on false positives first. The sort of unwritten rule is to accept a 5% risk of making that mistake. You'll also hear this called the significance level. And to balance that 5% risk on one side, the industry standard is to aim for 80% power on the other. What that really means is we're accepting a 20% chance of a false negative, of missing a good idea to find a meaningful effect. It's that sweet spot between being too risky and being too scared to change anything. And honestly, this quote from the Netflix team just sums it all up perfectly. The whole point of running experiments isn't to find some kind of absolute 100% truth, because that's impossible. The goal is to understand the uncertainty, to measure it, so you can make really smart decisions even when you don't have all the answers. So, at the end of the day, understanding statistical power isn't just for academics. It's what gives great ideas a fighting chance. It's the tool that helps us separate a real breakthrough from just random noise. And that kind of leaves us with one last big thought to chew on. How many world-changing ideas are out there right now, just waiting for a test that's powerful enough to finally see them?